Welcome to the first lecture of Physics 315. I wanted to get started by doing a little bit of review from what you learned in Physics 211 or whatever your equivalent electricity and magnetism class was. So there are a bunch of concepts we already know that are going to be useful in this class, so let's name them. So the first is voltage. We also call this electric potential in Physics 211, and we use a variable V for voltage, and it has units of volts, sometimes millivolts in this class, sometimes kilovolts in real life, but we won't probably run into kilovolts in this class, at least not very often. So important things about the voltage is that our voltage is defined at points in space, or in the case of circuit analysis, at points in the circuit. Now, an interesting thing about voltage is that if you have a circuit with voltages at different points, and you add some constant voltage to all of those numbers, meaning that 10 volts becomes 11 volts, and 12 volts becomes 13 volts, and 0 volts becomes 1 volt. Like, you add some number of volts to everything, the behavior of the circuit is not going to change. And so what I mean by that is the physically relevant thing, the important thing about voltage is voltage differences. It's not the absolute voltage number that matters, it is the difference between point A and point B. So, voltage differences are really the important thing to pay attention to here. So for example, if we have a component like a resistor, we can look at the voltage across this resistor. So that's what we say, the voltage across this resistor, or sometimes we call that the voltage drop of the resistor. And that is going to be the voltage difference between these 2 points. So that is, the voltage at this point minus the voltage at this point. So if it's, 5 volts and 0 volts, it's a 5 volt difference. If it's 95 volts and 90 volts, it's still that same 5 volts delta V difference. We can also look at the voltage difference between 2 points. So in the case of the voltage drop across the resistor, the 2 points are implicit. It's the points on either side of that resistor. We also could have something more complicated where we have some point labeled point A in the circuit, and maybe there's some circuit here that I don't know what it is, it doesn't matter. And then we have some point B, and this goes off to some other stuff. So we can also look at the voltage difference between point A and point B by, again, subtracting those two voltages. So this, we would call that the voltage difference between A and B, or the voltage drop between A and B, or the voltage drop across whatever this is. This could be a component in the circuit or a collection of components or something like that. All right, lastly, we also can measure, or I should say we can refer to voltages at a single point. So voltages at a single point are always implicitly being compared to something else. So if we talk about, we have some circuit, and I'm not drawing careful circuits here, and we have some point that's point A, and we say, what is the voltage at point A? What we're really asking is, what is the voltage difference between point A and the point that we have called ground? So the ground of our circuit is where we are defining the voltage is 0, so the voltage difference between some point and 0 is just going to be the voltage value at that point. So yeah, when we talk about the voltage at a single point, this something else is ground. We'll talk more about grounds later on in the class. For now, we just need to know that our ground is going to be 0 volts. All right, I think that sums it up for voltage. Let's talk briefly about current. Electric current, this pen is dying on the first day. That is not a good omen. So for current, we use the variable I. We have units of amperes, and The SI unit is amperes. It is very common. We will be using milliamps in this class, especially for the labs we're doing. You know, all of our currents will be in milliamps, and we won't have amps of current. So 1 amp of current. Well, before I write that, current is the rate of flow of charge through a, well, in the case of this class, a wire or an electrical component, and 1 ampere of current is equal to 1 coulomb per second of current flowing through there, coulomb being the SI unit of charge. So we have learned in other classes that when we have charge flowing through a wire, the direction of the current, so here's our wire, and we say, okay, it has a current flowing to the right, and what we learned is that what this actually looks like is a bunch of electrons, which are negatively charged, I guess I'll draw them as little minuses, moving to the left. These have velocity to the left, and this gives us this current to the right. Okay, so this is the whole difference between the electron current and what we call the conventional current. So the conventional current is the direction of current flow that you would have if it was little positive things moving in the wire. So even though it's negative things moving this way, we are going to stick with the conventional current. We are going to totally ignore the fact that it is negative electrons moving. We're going to pretend that it is positive charge moving, and I promise that this, I think, is the last time in the class we will have to address this. Surprisingly, we can do basically all of the electronics in this class without worrying about electrons, ironically enough, and just treat it as this imaginary positive charge moving through our circuit. All right, so we talked about how we can define voltages, you know, between two different points. With current, our current is defined through a section of wire or a component. This means that we cannot always define the current at a particular point in the circuit. So what I mean by that is we might have a junction or something where we have multiple different currents flowing, like the current is going to the right and then it splits into two parts here. So at this junction, at that junction, what is the current? Is it just this one? Well, that doesn't take into account these. It's definitely not like all of them added together or something like that. So anyway, at this point, I think the current is ambiguous, so we won't ask for things like that. We will make it very clear what is the current in, this wire, or what is the current entering this junction from the left, or something like that. So with currents, we always want to specify a wire or a component, not just a point. All right, lastly, we've talked about current, we've talked about voltage. We should talk about I think the easiest equation that has both of them in it, and that is Ohm's law. I'm going to switch pens here. So Ohm's law applies only to resistors. We'll talk more about resistors later. So a particular resistor has a resistance value R that relates the current flowing in that resistor to the voltage difference across that resistor by the following equation. Delta V is equal to IR. So again, delta V, the voltage difference between the two ends of the resistor, I, the current flowing through that resistor, R, the resistance. So for a particular voltage, high values of resistance mean you get small values of current, low values of resistance mean you get high values of current, since these have to multiply to be this same thing if we're imagining changing the resistance value. The delta V in this equation is implicitly between the two ends of the resistor. And I say implicitly because now we are going to do something that the people who are careful with their variables won't like, and we're just going to not ever really write delta in front of this, or at least we're going to often get away with not doing that, because when we're using Ohm's law, when we're talking about resistors, we are virtually always interested in the voltage difference across it. So whenever we have this is always a delta V across the resistor, and so we're just not going to write the deltas. It still means the voltage difference, but we're just not writing those deltas.